Hello fellow problem solvers. So today we're going to be doing a problem from number theory. This is a phenomenal number theory problem out to try if you're getting comfortable with your number theory skills, like you're almost at the IMO shortlist level, like you almost get to solve an N1, but you're not quite there yet. This is a phenomenal problem for you to try out then. And I suggest you try it out for a minimum of 45 minutes, ideally 2 hours to 2.5 hours, not more than 4 hours. If you'd like to go along with us, give it a go for the next 20 minutes. And now without further ado, let's begin. So we have sk is the sum of the digits of k, and an is the sum of the digits of 2 to the n. Does there exist an n such that for every n greater than n, we have an plus 1 greater than n? In other words, does there exist some n such starting from which this sequence is strictly increasing, right? The sequence an plus 1, an plus 2, an plus 3 is strictly increasing. So what does it mean that the sequence is strictly increasing? Well, it means that the sum of the digits of a capital N plus 1 is going to be less than the sum of the digits of that times 2. It's going to be less than the sum of the digits of that times 2 again, and so on and so forth till infinity. Now this is a very cool problem, and the idea is first, like, how do you even begin? Now, one approach you might try to play around is to start seeing like the sum of digits of 2, 4, 8, 16 till some number. That is what I did, and it didn't get me anywhere, right? It's because later down the line you don't know what is the sum of the digits of 2 to the millionth, right? You don't know, basically. And you have to prove really, maybe there's a way to prove, like this was my thinking, that I'll have a lot of zeros at some point, right? But that also seemed a bit difficult because you can't just have k zeros in the first k of these in the first half, say, because if you're starting from, when you get it to a 0, then you're saying like this other part is divisible by 2 to the n for this large n. And that as well is also iffy whether you can actually go ahead and prove that. So overall, a difficult problem to begin with. And it's difficult to approach it like that. So we need to start approaching it from a general standpoint immediately. Now, here for me, the idea is, okay, what do I have? I'll have some number, let's say. I'll have some an that starts off with a 1, right? And ends with some even number. Then I'll have 2 times an, starts off with either a 2 or a 3. Then has some numbers. 4 times an has either a 4, 5, 6, or 7. And then some other numbers. And then when I have 8 times an, I get, in every single one of these instances, a 1 again. Yeah. And now, actually, if it starts 7, yeah, anything only gives me a 1 again. So it seems, so I have an, 8 times an, and I'll be getting a 1 again, and then this can increase, then this is bigger than this. This is bigger than this plus 1 plus 2. This is at least 3 times. The sum of the digits here is at least 3 times smaller than the sum of the digits here. That's what we have initially. Now, when we also have sum of digits, and we're doing things with sum of the digits in base 10, it makes sense to look at what? I invite you here to pause for another 10 minutes and think about what else can you look at? And the answer is, you can look at modulo 9. Because modulo 9, what you have is, you have 2 to the n. 1 is going to be congruent. 2 to the 6n is going to be congruent to 1 modulo 9. And 2 to the 6n plus 1 is going to be congruent to 2. 2 to the 6n plus 2 is going to be congruent to 4. Then 2 to the 6n plus 3 is going to be congruent to 8 or minus 1, like the same thing. And then these will like go ahead in a cycle. But what do you also know from this? Like right now you have an, and 8 times an is at least 3 plus an. But here you have between, say, a6n and a6n plus 3, you have this number is at least 7, has 7 plus this. Like the sum of the digits is at least 7, the sum of the digits here. Like they can't be the same, so it must be at least 7 times that. And then if you go like a6n plus 4, we get from minus 1 or 8 till 16, which is congruent to minus 2, which is 7. And now what is the difference between these two numbers? The sum of their digits. Well, it's at least 8. Because this is 8, this is 7. We need this to be less than this. And so this number is at least 8 plus this number, like in their sum of digits. And then 2 to the 6n plus 5 is congruent to what? It's congruent to 7 times 2 is 14. 14 modulo 9 is 5. And then this one has at least 7 plus this. And then when we go to a6n, which is congruent to 1 modulo 9, this is at least 5 plus this, 6n plus 6. So we have an is going to be less than or equal to an plus 1, actually a6n is going to be less than or equal to a6n plus 1 minus 1. And then this is less than an plus 2 minus 1, actually an plus 2 minus 1, which is then less than or equal to, so this is less than or equal to this, a6n plus 3 minus 4 minus 3. And then from here to here, I get at least 8. So this is less than or equal to a6n plus 4 minus 8 minus 7. And then this is less than or equal to a6n plus 5 minus 7 minus what do we have? 15. And then this is less than or equal to a6n plus 6 minus 5 minus 22. So a6n is going to be less than or equal to a6n plus 6 minus 27. Like this, we always have this. And now with that, and this is also an, for an en is going to hold, this is going to hold true as well, because we're going to have the same sort of jumps. And now from here, I invite you to pause for another 20 minutes and see if you can combine this and this in some way, shape, or form. And now is the next time, here's the next idea. So we have, this is the case. However, we have this is 2 to the 6n, and this is 2 to the 6n times 2 to the 6th. This is 2 to the 6n times 64. Now, so this number is 64 times this number. But it has, the sum of its digits has to be 27 times bigger. Like it has to have, the sum of its digits is at least 27 times that. So my question is for you, how many digits do we add once we multiply? Actually, this is not an, this is 2 to the n. But the question is, how many digits do we add once we multiply by 64? And like roughly we add 2 more, sometimes we add 2 more digits. Sometimes we add only 1 extra digit. So these, both this and the fact that we add at most 2 digits, and that is sometimes we add 2 digits, cannot both simultaneously be true. Here we have 27, which is like you need sort of 3 extra digits, 3 extra 9s to like to be able to like keep this bound alive. So now here's where I invite you with this idea to pause for the next 20 minutes and try to push the problem further. Try to see if you can write this down in a nice way now. And here's the next step. So now what do we have? We have an plus 27 is less than or equal to an plus 6, right? And now what do we know? We know that inductively an plus 27 times k is going to be less than or equal to an plus 6 times k, right? So now let an have s digits. Then we have an is going to be, what's it called? Greater than or equal to, is going to be greater than or equal to 1, right? And an plus 6k has at most how many digits? At most we're adding 2 digits every turn. At most s plus 2k digits. And so an plus 6k is going to be at most equal to what? Well, it's at most going to equal to 9 times s plus 2k, where s is a constant. And so now we have for every k that we have, and this is greater than or equal to then 1 plus 27k. And now for every k, we have that 1 plus 9k is less than or equal to 9s, where s is a constant, and that is the number of digits an has. The number of digits 2 to the n has, right? Not an, but rather 2 to the n. So can this always hold true? And the answer is no. For k is equal to s, this thing doesn't hold true, and we've reached a contradiction. Now, I like this problem a lot because it has, you can't just do immediately, oh, let me look at the first couple of numbers and get a pattern, but you're forced to look at things in general. And then this thing with the sum of the digits of n, I really like the fact that we need to use modulo 9, right? Because that is the thing you use in general when you're dealing with sum of digits. It's a tool you use. And it's used here in a way to help you estimate the members of these sequences. And then from there, you're able to estimate this size versus this size, and you're able to recombine the two. So I think this is a very, very, very cool problem in that respect. And I like it, And this finishes up our problem. And as always, thanks for problem solving.